This video is going to outline another application of Hess's law, this time to calculate the enthalpy change of solution. So, first of all, what is enthalpy change of solution? Well, it's the energy change when 1 mole of an ionic compound is dissolved in water to give a solution of infinite dilution. The key bits in this definition are 1 mole of the ionic compound and dissolved in water to give a solution of infinite dilution. Before we try and write an equation for this enthalpy change, it's first worth considering what we mean by an infinite dilution. To understand this, let's consider what happens to an ionic compound when it dissolves in water. Let's take a made-up ionic compound XY. And let's assume in this ionic compound that X has a positive charge and Y has a negative charge. So when this dissolves in water, what actually happens is that both of the ions end up being surrounded by water molecules. And water molecules are attracted to the ions because water molecules are polar, and therefore the partially charged sides of the water molecule will be attracted to the ions. So the positive X ions will end up being surrounded by the partially negative side of water molecules, and the negative Y ions will be surrounded by the partially positive side of water molecules. So once dissolved in water, the ionic bonds between the positive X and negative Y ions have effectively been replaced by attractions from the water molecules. Now at the moment, because my ions are still close to each other in the water, we'd expect to see some attraction between those ions. So in order to make an infinite dilution, I need to add enough water molecules to be able to separate those ions so there are no longer attractions between them. The attractions remaining are only between the water molecules and the ions themselves. You won't need to be able to explain this for IB chemistry, but it's useful to know. So let's now try and represent the enthalpy change of solution in a chemical equation. I need to show 1 mole of an ionic compound. Let's take XY again, and it's going to produce the dissolved ions in solution. So, if I can't calculate that enthalpy change of solution directly, Hess's law states that I can take an alternative route. So in the case of enthalpy changes of solution, the alternative route we're going to take is going to have 2 steps. The first step is the enthalpy change of lattice, or lattice enthalpy. Let's consider the definition of lattice enthalpy. It is the energy required to separate 1 mole of an ionic compound into its gaseous ions. Again, the key parts to this are 1 mole of the ionic compound and gaseous ions. So, if that's the definition, let's write the midway point of our alternative route to calculate enthalpy change of solution. Here you can see I now have X plus ions in the gaseous state and Y minus ions in the gaseous state. We would expect values for lattice enthalpy to be big positive numbers because it's going to take a lot of energy to separate my ionic compound into gaseous ions. The final step then is to get from gaseous ions to ions dissolved in solution, and for this second step we're going to require 2 separate arrows, one for the X plus ions and one for the Y minus ions. And dissolving gaseous ions in water is known as enthalpy change of hydration. The red arrow is enthalpy change of hydration for the X plus ions, and the blue arrow is the same process for the Y minus ions. Let's write a definition for enthalpy change of hydration. It is the energy change when 1 mole of gaseous ions is dissolved in water to give a solution, once again, of infinite dilution. Once again, the important bits here are 1 mole, gaseous ions, and a solution of infinite dilution, as we explained before. If I know the values for my alternative route to calculate the enthalpy change of solution, all I need to do is add my lattice enthalpy to the enthalpy change of hydration for the positive ion, and then also the negative ion. And according to Hess's law, that's going to give me an accurate value for the enthalpy change of solution. Let's now summarize the key points in this video. In order to calculate the enthalpy change of solution, I can find an alternative pathway by first finding the lattice enthalpy for my ionic compound, which would break apart my ionic compound into its gaseous ions. And then I can use enthalpy change of hydration data for the X plus and XY gaseous ions to get across to the products of my enthalpy change of solution. You need to know the definitions of each type of enthalpy change, and you might also be asked to calculate it when given the data. Hopefully, this video was of some help.